Hello, calculus students and general seekers of truth. Welcome to the lesson on the ratio and root test. And so we've learned a lot of tests up to this point to determine whether or not a series converges or diverges. And this is yet another arsenal that we're going to add to our toolbox here in order to manage and understand series better. Okay. So this time I'm going to start out by telling you what the ratio test says, and then we'll kind of unpack it a little bit. So given an infinite series with non-zero terms, so you can't have a bunch of zeros mixed in there. You'll see why in a minute. Then we can look at three distinct scenarios. In all three of them, we are looking at this limit right here. Okay. So what this is saying is that we are comparing each term to the term before. Okay. So this is another word of saying compare each term to its predecessor. Okay. And there are three cases. If in the long run the ratio between the current terms and its predecessor is getting smaller, then the series will converge absolutely. If the ratio between the current term and the previous term gets larger than 1, then it's going to diverge. And if it happens to be equal to exactly 1, then the result is inconclusive. You got to try some other test. Okay. So let's kind of unpack what each of these cases is saying a little bit more. So if I look at case 1, okay, all that's really actually I'm going to do it down here. Okay. If I look at case 1, all that's saying is that as n approaches infinity, okay, in other words, as n gets really, really large, okay, the ratio, or each term, I should say this in a better way, okay, each term is a fraction, a proper fraction, of the term that came before. Okay. So as this may not happen earlier on yet, but eventually, if you keep going, okay, each term will become a fraction of the term that came before. So if you compare this to a geometric series, okay. So let's just look at what a geometric series says as an example here. So if I have a geometric series, let's something like this, 1/3 to the nth, n equals 1 to infinity. Then I start listing this out, and I see that I have 1/3 plus 1/9 plus 1/27 plus 1/81, and so on and so forth. Then if we compare the ratio of each of these terms, right? So if we compare like a sub n plus 1 over a sub n, then what we end up here is 1/9 divided by 1/3, okay, and then 1/27 divided by 1/9, and then 1/81 divided by 1/27. Okay. So if we were to make this comparison, we end up with 1/3 every time, right? So for a geometric series, if the ratio between each of the terms is less than 1, then the series converges. Otherwise, it diverges. So that's what this first statement is really saying, is that eventually, if you go on here, the series may not be geometric, but this first statement is saying that if you keep on going further and further down, that eventually it looks like a geometric series because the ratio between any of the two terms is less than 1. It's a proper fraction. Then it will converge. Okay. In case 2, well, it's the same thing. If the ratio between each of the terms is greater than 1, then it will diverge. So case 2 is even simpler. It's a way of saying that the terms are getting larger. Okay, so an example that we can compare it to the geometric series is, what if I have like 1.5 to the nth? Well, if we list out all these terms, then we end up with 1.5 plus 2.25 plus 2.25 times 1.5 plus 2.25 times 1.5 squared. Okay? So each of these terms are getting larger and larger. That's effectively what statement 2 is saying. That we don't know what, and the limit here is just trying to say that we don't care very much what the series looks like at the beginning. We care about what it looks like in the long run when n gets really, really large. So if as n gets really, really large, each term is getting larger, then the series will diverge. And in the third case here, if it happens to equal exactly 1, then the test is inconclusive. So let me show you case 3. Right? This is just some justification here. Case 3. So if we consider this very famous and familiar series at this point, okay, and we take the limit of, as n approaches infinity, of a n plus 1 over a sub n, then a of a sub n plus 1 is just the next term, so 1 over n plus 1 divided by 1 over n. So this comes out to the limit as n approaches infinity of 1 over n plus 1 times n. Okay. And you can see here that this limit will eventually approach 1 if you look at the leading term, but this series, we already know it diverges. From previously, we know that this diverges because it is a harmonic series. Okay. And now I'm going to show you another example of a series where the limit is equal to 1 and it actually converges. So we just take n squared, 1 over n squared. We already know that this series converges. Okay. Because it is a p-series, a convergent p-series, where p is equal to 2. Okay? But if you were to take the limit of the n plus 1th term divided by the limit of the nth, divided by the nth term, you end up with 1 over n plus 1 squared divided by 1 over n squared. And this will end up giving us the limit as n approaches infinity of, let me use a different color here, 1 over n plus 1 squared times n squared. And this limit will also approach 1, okay, in the long run. So you have two examples here. In both cases, the limit of the two consecutive terms are both equal to 1, but in one scenario it diverges in the case of the harmonic series, and in the other scenario it converges in the case of a convergent p-series. So that's just an example to show you why the third case here would be inconclusive. The first case is conclusive that it will converge because in the long run it's going to behave like a geometric series. Okay. The second case, it's going to diverge because it will also behave like a geometric series, but with each term getting larger and larger. Okay. And the third case is inconclusive. So if you use the ratio test and you end up with this scenario, then that just indicates you have to try some other tests. Okay, so that's a brief introduction here into the ratio test. Let's look at another video that deals with some specific examples.